Hi, today I'm talking about LeetCode problem 1382, balance a binary search tree. This problem asks you to write a function that will take a binary tree and return a balanced tree. And what they mean by balanced tree is it's balanced if and only if the depth of the subtrees of every node never differ by more than one. So what does that mean? It means we can ask, what's the depth at the left branch and the right branch? Left branch is obviously 0. There's no nodes on the left branch. The depth of the right branch is 1, 2, 3. So the difference between the left branch, 0, and the right branch, 3, is more than 1. This is not balanced. But you can also apply that same analysis at every node. On the second node here, the difference is between 0 and 2, so that's not balanced. Here, the difference is between 0 and 1, so that is balanced. So this subtree would be balanced, but every other subtree would not be balanced. So that's what we mean by balanced. And their example gives us, okay, you can take this subtree and turn it into a balanced one like that. They also say in the code that if there's more than one, or sorry, not in the code, they say in the problem description that if there's more than one answer, you can return any of them. So you can see how there might be multiple answers. Here I just drew another answer compared to what they give as an example. And you can see, this subtree is balanced, this subtree is balanced, this subtree is balanced, and this subtree is balanced because the depth of the right-hand side is 1 compared to 2 here, or it's 0 and 1, or it's 0 and 0. So all the subtrees are balanced as well. So I thought of a couple ways you could do this. So one way I thought of was constructing a new binary search tree and using the add function on your new binary search tree in such a way so that you always added to it when it was balanced. And then you just go through the input and say, okay, I want to add a 1 to my new binary search tree. I want to add a 2. And when you tried to figure out how to add the 2, you would only add it in a way such that the tree remained balanced. So I was trying to think about how would you do this? How would you write the add function? And it occurred to me that your input might be in such an order that you would need to rebalance the tree. So if a 3 came in, if I was building up my balance tree, 1, 2, and then a 3 came in, how would I handle that? I'd need to know to say, the output would look like 3, or what I would want the output to be would be something like 2 in the middle, and then 1, and then 3 over here. There's a balanced tree. But how do I know, adding the 3, that I need to pull the 2 up to the top and then have the 1 be on the left and the 3 on the right? It seemed a little complicated and also a little slow because I'd have to be potentially rebalancing the tree every node I added on. So in their example, this is basically a linked list, right? Just if this went on for 10,000 nodes, every node that I add, I would need to rebalance my tree. And that didn't seem like a great solution. So the other way I thought of would be to turn my binary tree into a list. Here, step 1, turn the binary tree into a list, and then turn the list into the balanced binary tree. And that seemed a lot easier, and it seemed consistent. So basically what I would do, let me look at my example again. What I'd do is I'd take this example and I'd turn it into a list of just all the numbers in the tree. So 1, 2, 3, 4. And then I'd turn that list into the balanced tree. And how do I do that? Well, basically, you're just going to pick I have an illustration of this already as I reasoned out how I would do that. Basically, you just pick the midpoint and you add the midpoint, and then you add the left-hand side and the right-hand side. So in my example of 1, 2, 3, 4, I'm going to pick the midpoint, which is 3. That's just the length of the list divided by 2. I pick the midpoint, and then I'm going to follow the same procedure of adding my list to a binary tree on the left-hand sublist and on the right-hand sublist. So for the left-hand sublist, I'm going to pick the midpoint, which is 2, and I'm going to add 2. And I'm going to add them, according to the rules of a binary tree, where if the value I'm trying to add is less than my current value, I'm going to add it to the left. If the value is greater than, I'm going to add it to the right. So my first one is 3. I'm going to add a 2. That goes to the left of 3. And then I'm going to add the sublist left of 2. And I would add the sublist right of 2 if there were anything there. So the sublist left of 2 is just a 1. I'm going to add that. I'm going to add the left and right sublist. There's nothing there. And then I'm going to finish up by adding the right sublist of 3, which is just 4. And it produces that, which is also a balanced binary tree. So I followed the same procedure, here with a longer list, 1 to 10, just to make sure this would work. So I have the numbers 1 to 10. That's length 10. So the midpoint is 5. So I take, let's see, the fifth index, 0, 1, 2, 3, 4, 5. I take this, 6, and that goes, as to the root of my new tree. And then I'm going to create the sublist on the left, and I'm going to add that. And I'm going to take the sublist on the right, and I'm going to add that. When I add the sublist on the left, I'm going to find its midpoint. That's 5 divided by 2, integer division. So that's 2, 0, 1, 2. So my next node is going to be a 3, and you can see that here on the left. And so just following that procedure, I demonstrate to myself that it does build out a balanced binary tree. So you can see that each sublist here is balanced. 0, 0, 0, 1, 0, 1, 0, 1, 0 for their left right-hand lengths. You can see that each of the subtrees are balanced. So let's implement that algorithm. Here's the function they ask me to write, balance BST. And you can see the first thing I'm going to do, I'm just going to create a tree list. This is the list of all the values in the tree. I'm going to sort the tree list so that I know it's in order, so I can easily pick the midpoint. And then I'm going to create something called the result, which is going to be a new binary tree that I'm going to return. I'm going to create that by converting my list into a tree, and then I'm going to return my result. So let's step into the getList function. This is how we turn our input binary search, or our input binary tree, into a list. GetList. So here it's a recursive function, and what it's going to do is it's going to say if the root, or the node that I'm at, is null, then my answer is just whatever the result list I've been building up is. Otherwise, assuming it's not null, I'm going to add to my result list the value of root, and then I'm going to recursively call back into the getList function with the left and right hand nodes, and then I'm going to return my result. So if we want to illustrate that, we would say 3, 2, 4. If we were doing it with this, our root would start at 3, and our result list is going to start as an empty list. We would make the check, is root none? No, that's not true. Root is 3. So okay, we're going to add 3 to our result list, and then we're going to call our getList function with the left and the right hand. So in the subsequent call, we're going to call it like this, and we're going to use the same result list. Root is not null, so we're going to add 2, and then we're going to call it with the left, which would be root pointing to nothing, and the result list of 3 and 2, oops, which would, because root is none, would cause us to just return out, as you see on line 4. We're just going to return back the result list to the caller. And then we're going to complete the right-hand side, which is basically the same thing. The right-hand side of 2 is none. So we're going to return back the root list again, or sorry, the result list again. And then we'd handle the right-hand side. So this would settle the left-hand side. And then we call it for the right-hand side of 3, which is just going to do a very similar thing with root pointing to 4. And it's going to add 4 to our result list. 3, 2, 4, and then we'd be done. So that's how we're going to recursively build up a list of all the values in our tree. We've done that, so we have the tree list. We sort the tree list, so the tree list is in order. That's going to make it easy for us to pick out the midpoint of the tree list every time. And then we're just going to produce a new balanced tree from our list. So the balanced tree, the list to tree function, is going to take our tree list. Actually, as I have it written here, it's slightly more complicated than it needs to be. So let me just look at my submissions to find, oops, if this would load, to find a slightly simpler version of this same solution. Here it is. Yeah, the simpler version of this solution is going to work just like I drew it on the whiteboard. We're going to say if the length of the list we're trying to convert into a tree is less than 1, meaning the length of 0, then we're just going to return the tree, the current tree that we've been building up so far. So if we're trying to convert an empty list to a tree, we're done. Whatever we are at so far is what we're done. Otherwise, assuming we're not trying to convert an empty list, we're going to find the midpoint. So that's the length of our list, integer divided by 2. Yep, that's the midpoint of our list. And so then what we're going to do is we're going to say, we're going to add our current value to the tree that we're building up. And I'll walk through the add function in a minute, but it's just going to be doing a binary tree add. We're going to get the value at the midpoint from the list that we want to convert into the binary tree and add it to the binary tree that we're building. And then we're going to recursively call the same function with the sublist. So the sublist up to the midpoint and the sublist of everything after the midpoint, building up the same binary tree cur as we recursively call this function. So the add function is going to be pretty simple binary tree logic, pretty standard binary tree logic. If the tree that we're trying to add to is null, or if there's no value for the tree, then we're just going to return a new tree node with the value that we're trying to add. So that's like saying, I want to add a 5 to an empty tree. Okay, what that is a tree of 5. In line 20 here, we're saying if the value is greater than the value of my current tree node where I'm adding, then basically I want to add my value down the right-hand path of the tree. So this would be like I'm trying to add a 5, and the current tree value is only 3. So I want the value that I'm adding, 5, to be on the right of the tree. And so it's just going to check, okay, well, do I have a right-hand path? If I don't, if my right-hand path is none, then I can just settle this right here and say my right-hand path becomes a new tree node with the value I'm trying to insert, and then I'm done. If I do have a right-hand path, then obviously I don't want to insert the value I'm trying to add in the way I'm doing in line 22. Instead, I just want to recursively call the add function on the right-hand path. Yeah, so I'll kind of descend down the right-hand path and add my value there when I find a child that is null, or that is none. And then the other possibility would be that the value I'm trying to add is not greater than the tree's value. in which case I'm going to descend in the same way, the same recursive pattern, down the left-hand path. That is, if your left-hand child is null, we can go ahead and insert the left-hand child as the value we're trying to add. If the left-hand value is not none, then we'll recursively descend down the left-hand path on the add function. And so that logic is, what led me to, or that logic is going to be what solved the problem for me. Now, in terms of test cases, they give this one example test case, but I actually found it somewhat difficult to come up with meaningful test cases, just because it's a little awkward to like type in the test cases into this test case editor. But the test cases I'd want to see, okay, we have the right-hand path linked list. I'd like to see the left-hand path linked list. I'd like to see just a random tree, so like a tree that's not a linked list, but that has children. I'd like to see a tree that's already a balanced search tree and a tree that's not a balanced search tree. And then I'd like to see a tree that has the maximum number of nodes. And I'd like to see, so in my implementation, there's not really a worst case scenario. Like we're going to do the same thing every time. We're going to read the entire tree into a list, then we're going to sort the list, then we're going to read the entire sorted list into a new tree. So there's not really a structure of the tree that would pose a unique problem for me. But if I had a different implementation, then I'd want to make sure I was testing the worst case for my implementation. For this implementation, I think the worst case is just having the maximum number of nodes, which is between 1 and 10 to the 4th. So those are the test cases I'd like to do. When I submitted this code, it's getting something like 5 percentile for speed, which is very poor, obviously. Which is very poor, obviously. I started to think about how I could improve this, how I could make this faster. It seems to me that this is going in log n time. Basically, the step to convert the input binary tree to a list, that's just going to visit every node recursively. So that's in steps. Sorting it is in log n. The sort algorithm, that's the runtime of sort. And then, let's see, the list to tree is going to be the same thing. It's going to be, I believe, linear as well. So because I can just, because I'm going from a sorted list, I know exactly I need to take the input list, I need to take the midpoint, that's my new root, and then I need to add the left and right hand path. So I think the runtime of this is in log n. I looked at the discussion section for this problem to see someone else's solution, and I saw someone else reported they had in log n runtime, and I just copied this solution and ran it as well, and it wound up being like 5 times slower than what I had. So I'm pretty sure my runtime is in log n. There's bound to be a something even better than that though, because obviously I'm pretty slow for speed. I think like one easy way to speed it up would be, rather than dividing the list every time or like creating sublists, to just manipulate indices. So like using the start and end. I assumed that would speed it up because it means I wouldn't have to split the list every time or create new sublists every time. So that might be a little more efficient. And then I think I could probably be a little bit more efficient in the add algorithm, so that I wouldn't have to recursively call every time. But I haven't made those optimizations, though I haven't made the optimizations around the add algorithm, though I think I could to get substantially faster. But anyway, that's it from me for this problem. If you enjoyed this video, let me know. Click the like button. If you want to see more LeetCode problems solved like this and walked through, you should subscribe. Thanks for your time. Bye-bye.